Welcome to this heat transfer video lecture where we are going to continue talking about external convection. Specifically today we're going to talk about turbulent flow correlations. So if you recall from previous video lectures, we went through the similarity solution where we were able to, well, we didn't really solve it, we were able to observe the solution for laminar flow over a flat plate, and that required, getting to that solution required simultaneously solving the energy balance and the momentum balance and the continuity equation, which are all PDEs, so it's three coupled PDEs, and that made for some fairly complex math. So that was for the laminar region. So if you recall, for fluid flow over a flat plate, the Reynolds number is a function of x, or distance from the leading edge of the plate. So as that Reynolds number grows and as that boundary layer keeps getting thicker and thicker, eventually you start getting more circulation in your flow, as you see here, and the flow transitions from this laminar region. It goes to a transition region and then ultimately a fully turbulent region, and this changes the heat transfer properties quite dramatically when you transition from laminar to turbulent. As complex as that similarity solution was for the laminar region, you can imagine that it's actually getting a solution would be much more complex for this turbulent region. And so typically we would be looking at empirical correlations when you have more complex geometries and turbulent flow. So the way to get an empirical correlation would just be to do an experiment. You may have something like a heated plate, and you may be flowing fluid over that plate, just taking measurements of the surface temperature and the fluid temperature and knowing how much heat you're putting into your heating element. So you run these types of experiments, you generate a bunch of data, and then you would typically fit a Nusselt number correlation to that data. Typically, the Nusselt number is a function of the Reynolds number and the Prandtl number, with these other parameters, C, M, and N, being coefficients that result from that curve fitting. And you can see these plots. So here we have the log of the Nusselt number plotted versus Reynolds number. You can see different plots depending on the Prandtl number of the fluid, but you can actually lump those together. And if you're looking at instead the log of the Nusselt number over the Prandtl number, you see that all the data follows into this nice straight line. So the main takeaway from this is that experimentalists and people who do these kind of studies can group things together based on Reynolds number and Prandtl number, and you can actually come away with a correlation that is applicable for a lot of different types of fluids and a lot of different types of flow conditions, and you can get all those to fit nicely and give you a reasonable fit. However, if you notice, this line isn't perfectly accurate. There's still noise in the data. There are a lot of inaccuracies with these, so just keep in mind that these correlations may not always be perfectly accurate, and you may actually see plus or minus 25% uncertainty in some cases. So when we are talking about turbulent flow, or for a flow over a flat plate, we actually have to account for the laminar region as well as the turbulent region. So I mentioned that turbulent flow dramatically changes the characteristics of heat transfer. So in most cases we would see that our local Nusselt number and our local convective heat transfer coefficient would be much higher in the turbulent region. So when we're talking about getting an average heat transfer coefficient or Nusselt number over that entire region, we have to consider both regions, and this is typically done with an integration. The critical Reynolds number when you have flow over a flat plate is 5 times 10 to the fifth, or 500,000. I think it's very important to note that this is very different than the critical Reynolds number when you have flow through a pipe. And also another key difference is that because x is a variable and x changes as you go, the Reynolds number changes, so that describes the point at which your fluid characteristic changes from laminar to turbulent. So generally, the rule of thumb is 5 times 10 to the fifth is the critical Reynolds number. So that critical Reynolds number usually occurs at a critical distance. So that's denoted here as this x sub c. That is the critical distance. And so that critical distance is just the point at which your Reynolds number transitions from your Reynolds number crosses this 500,000 line, unless there's some other extenuating circumstance, like if there's something else that induces turbulent flow, then your critical X would change. It would be whatever point at which your flow changes from laminar to turbulent. So if there are no obstructions, then it just changes at 5 times 10 to the fifth. But often you can have what's called a tripped flow, where you may have, let's say you had some kind of obstruction here. So naturally, you'd expect these streamlines to really disrupt the flow. So in that particular case, your critical X may be here, and it may be sort of independent of the Reynolds number. So you may have to modify correlations to account for your fluid flow being tripped or transitioning to turbulent prior to you actually reaching this critical Reynolds number. And again, that is called tripped flow. So turbulent flow generally does get much more complicated than laminar because of all that extra circulation. You would have to typically do pretty complex CFD kind of calculations to really be able to analytically model what's happening in this region. So generally you cannot find analytical solutions and you have to rely on correlations, as I showed on the last slide. So we use these empirical correlations. So empirical means derived from data or from an experiment. So you may not always have a ton of physical insight into what those correlations mean. Just know that they came from people doing very carefully planned experiments. So I want to remind you how to find H. Again, this is a central theme for all of convection. So first you evaluate the geometry. Are you looking at flow over a flat plate, around a cylinder, banks of tubes, etc. As you go through the textbook, you'll find a lot of these different types of correlations. So it's just a matter of finding the right correlation for that particular set of circumstances. In addition to the geometry, you also have to know how is the fluid flowing. Again, if the flow is laminar or turbulent, that dramatically changes the heat transfer characteristics, and often you may have to use a totally different correlation for laminar situation or turbulent situation. We will evaluate the Nusselt number using that correlation, and that could be local or average depending on what's available and or what you actually need. And finally, you would back solve from the Nusselt number to find your H, using that relationship that the Nusselt number is equal to H times your critical dimension over the fluid thermal conductivity. And again, H can be local or average. So let's take a look at this for that turbulent flow case. So based on empirical correlations, researchers have found that this correlation tends to work pretty well when you have turbulent fluid flow over a flat plate. However, if you recall, we have this, first we have a laminar region and then we have a turbulent region. So the way to find the average heat transfer coefficient over that entire region would be first to find the local heat transfer coefficient for the laminar region and then the local heat transfer coefficient for the turbulent region, and then you would do this integration to average the two. So you'd be integrating from 0 to x sub c, where x sub c is your critical x when the flow transitions from laminar to turbulent. So you're basically just integrating h over the laminar region, and then you're integrating h over the turbulent region, where this integration on the turbulent region is going from your critical x up to the full length of the plate. This CF, I should mention, is the friction coefficient from fluid mechanics, so that does play into it. We typically won't deal with that much mathematically, just know that the fluids that happens is important. So as you do this integration over a normal set of circumstances, you would come away with an average Nusselt number correlation looking like this. So this is assuming that your critical Reynolds number is 5 times 10 to the fifth, meaning that there's nothing disrupting your flow prior to you reaching this Reynolds number as a function of x. So assuming this number, that gives us this 871 parameter. However, if your fluid flow was tripped at the leading edge of the plate, where your critical Reynolds number would be 0 and your critical x would be 0, then this 871 term goes away and your whole entire plate is all in the turbulent region, and you end up getting this correlation, which is just basically the integration of this guy over the entire length of the plate because the flow is turbulent the entire way. So basically xc would be 0, so you'd get rid of that and you'd just be integrating this part to give you this equation. So again, there's a lot of correlations throughout this material, so it's really just a matter of finding the right correlation, making sure that the particular characteristics of your problem match with that correlation so that you know that you're applying a correlation that is reasonably accurate. Other circumstances, so if you have fluid flow over a flat plate, but the entire plate is not heated, you can get what's called an unheated starting length. So this Greek letter she characterizes the unheated starting length. So here in this region, you would have your surface temperature would just be equal to your bulk fluid temperature or your free stream temperature. So there would be no heat transfer happening in this region because they're both the fluid and the surface are at the same temperature. However, you would start to develop the velocity boundary layer because of all the viscous forces that are happening. So if we did have heat applied to this part of the plate, only at that point would you start to develop this thermal boundary layer. So this is called an unheated starting length. And you'll see the acronym on the next few slides as USL, unheated starting length. So I mentioned this before. So the value of the critical Reynolds number depends on the free stream turbulence and surface roughness. So normally that critical Reynolds number is 5 times 10 to the 5th. If you did something at the leading edge to trip that flow, you may see turbulence early on and your flow would be turbulent throughout, which is something we've already talked about. So other surface conditions might include uniform temperature. So you may have the entire plate at the same temperature, or in a different circumstance, you may have uniform heat flux. And then, as I mentioned, you could also have this unheated starting length, which is this distance represented by the Greek letter she. So just a bunch of different variations on fluid flow over a flat plate, and many of these different circumstances come with different correlations. So here are some correlations. So depending on whether you have an unheated starting length and or uniform heat flux, and also depending on whether your flow is laminar or turbulent. So we're basically going to be using this correlation in those cases. So this modifies the turbulent flow correlation that we talked about. So what you do here is you first evaluate the Nusselt number as if there were no unheated starting length. So you just use this correlation. So first use that correlation, evaluate the Nusselt number as if there were no unheated starting length. So use this bottom correlation first. Then you take this number, so that's just an evaluation of the Nusselt number, assuming that your unheated starting length she is 0. Plug that in to the top, and then you would account for that unheated starting length by plugging things into this correlation below. And you notice these different parameters, A, B, M, and C. So you can look up what those parameters are using a table like this on the right. So whether your flow is laminar or turbulent and you have a uniform surface temperature or uniform surface flux, which would be the plate condition, and then you would apply the unheated starting length here. So it's really can be a little bit confusing. There are just kind of some messy equations. That's just kind of the nature of convection. You get these correlations determined experimentally because really the math to actually figure this out using fundamental principles of fluids and heat transfer is just really too complex and outside of the scope of this class. So getting more into this special case, to calculate flux and or temperature depends on the condition. So if you have a uniform surface temperature, meaning that your plate is all at this uniform temperature Ts, well, outside of this boundary layer up here in our bulk fluid, we have that our bulk temperature is also uniform throughout. So if this temperature is uniform and T infinity is uniform, notice that H is going to be changing. So H will be localized, which means that our value of the flux would actually be different, and it would be a function of our H. So you could solve for the flux. So if you have a uniform surface temperature, notice that your flux is going to be localized, and your flux would vary depending on where you are on the plate. To get the total amount of heat transfer over the entire plate, you could rather use the average heat transfer coefficient and then just plug that into this to Newton's law of cooling. So the key takeaway here is that because your H is localized and it's a function of x, your Q may be a function of x if your surface temperature is indeed uniform. So you would use the correlation shown here on the left, and if you have laminar flow throughout, you would use an exponent of p equals 2. If you have turbulent flow throughout, you'd use an exponent of p equals 8. And then getting your average heat transfer coefficient, again, would require this numerical integration for laminar and or turbulent flow. So in the laminar region, you would do the integration using the p equals 2 exponent correlation, and then in the turbulent region, you would do the integration using the p equals 8. Then you would average those out using this total equation to get the average heat transfer coefficient. Okay, so the other situation might be that you have a uniform surface flux. So if you have a uniform surface flux where you have this Q and it's being applied uniformly throughout the plate, well, you still have up here in the bulk, you still have a constant temperature T infinity outside of that boundary layer. So that tells us that the plate's surface temperature must be a variable. And again, we could use Newton's law of cooling to go and solve for what that surface temperature actually is. And we could get the total amount of heat transfer just by taking our constant uniform flux and multiplying that by the entire surface area. Again, a key takeaway here is things can be localized, and you might, because things may be different, if you're looking at a piece of the plate here versus a piece of the plate here, you actually want to be really careful that you use the flux version of Newton's law of cooling, and generally to get the total amount of heat transfer would require us to use the average rather than the local. So just be sure, because everything is changing, our Reynolds number changes, our heat transfer coefficient changes in a function of x, you can't just apply Newton's law of cooling assuming a constant h the whole way. You have to apply it locally to get the flux for that particular local point, or you could apply it on an average basis to get the total flux using the average heat transfer coefficient. But this bottom relationship here, Newton's law of cooling, doesn't really give you specific local information. To get that, you'd have to use the flux version. Using these correlations for turbulent flow over a flat plate, you'll be looking up information to get like the Prandtl number and the viscosity and the density. So those can typically be temperature dependent. So because the fluid temperature may be changing, it is changing as you go. Typically, the rule of thumb is that you want to evaluate the fluid properties at what's called the film temperature. The film temperature is the average of the plate temperature and the bulk fluid temperature. So it's the surface temperature plus T infinity divided by 2 to give you the fluid temperature. So a lot to take in, a lot to digest, and a lot to swallow. The math of convection isn't nearly as pretty and sophisticated as it is for conduction. So it's actually much more messy and much more complicated, so we end up doing these empirical correlations, and that's, you get some really useful information out of them, but unfortunately there's not typically a ton of physical meaning behind those equations other than someone did an experiment, generated this data to fit this empirical correlation. But these are just some more examples of the various different types of geometries and fluid flow conditions and heating conditions that you might encounter as you're trying to find H.